Hello, and welcome back to this series on modern quantum chemistry. In this video, we will cover operators and matrices. And as a joke here, I put the heat operator on the bread vector as leads to the toast vector. You understand why later. So, all that an operator is that something that converts a vector into another vector. Or mathematically, we write O hat operator on the vector A gives you the vector B. And in this course, we'll be dealing with linear operators, which means that when you operate a vector, when you run an operator O, which is linear, on a linear combination of vectors alpha A plus beta B, you'll get alpha OA plus beta OB. A linear operator is completely determined if what vector the operator turns a given vector into is known for all vectors. If a vector is represented by a basis set EI equals E1, E2, E3, all that is needed is what the operator does to each basis vector. Operators can be written as matrices, and when they are, when you operate when you operate an operator O on a basis vector EI, it can be written as sum over all j indices of EI times OJI, or if you operate that on EJ, it is sum over all indices of EI times OIJ. And it doesn't matter how you write it, since I and J are really dummy indices. So you can write OJI as a matrix, and for your visualization, I wrote the components of O down in the matrix. Now let's say that you have an operator C, which is basically the given operator when you first run operator B on a vector and then run operator A on the result of that. So I can express that as C hat EI is sum over all j of EJ times CJI, or it's the same thing as operator A acting on the result of operator B acting on the basis vector, which gives you operator A times sum over all j of EJ times BJI. And since A is a linear operator, you can take that operator under the sum to get sum over all j of A hat EJ times BJI. And operating A hat on EJ, you get sum over all k of EK times AKJ. Notice I did not use the same index. I used a different index K, since J and K are not necessarily the same when you expand the product out, or when you expand the operator out. Now, since J and K are dummy indices, you can switch J and K to get since BJI is not dependent on K, you can take BJI under the sum to get sum over all J, sum over all K of EK times AKJ times BJI. And since J and K are dummy indices, you can switch J and K to get sum over all K, sum over all J, EJ, AJK, AJK, BKI, which is the sum over all J, sum over all K of EJ, AJK, BKI, which if you remember is equal to the sum over all J of EJ times CJI. And you can rewrite the sum as sum over all J and then put the other sum in the parentheses, which is equal to the sum of all J of EJCJI. So for each component of K from these two sums, you would get sum over all K of EJ times AJK times BKI, which is equal to EJ times CJI. And since J is not dependent on K, you can take EJ out of the sum to get EJ, sum over all k of AJK BKI equals EJ times CJI. And which would lead to sum over all k of AJK times BKI equals CJI. And if you remember from linear algebra, this is the definition of matrix multiplication. So if you define an operator C as first operating operator B on a vector and then operating operator A on the result of that, C is exactly A times B. We represent it all as matrices. And a final note on matrix multiplication: it is generally not commutative. And matrix, and when something is commutative, that means the order doesn't matter. So when you operate A and B on a vector, it is the same result as when you operate B and A on a vector. So let's define the commutator of two operators A and B as A times B minus B times A when A and B are matrices, and it equals 0 if A and B commute. Now let's define the anti-commutator, which is represented by curly braces instead of those brackets, as A times B plus B times A when A and B are matrices, which is equal to 2 times A times B if A and B commute. Well, that is it for this week, and I hope you have a great weekend, and stay safe.